Welcome back to Equilibrium. In part 2 of this unit, we're going to be looking at type 2 and type 3 equilibrium problems. This entire video is full of math problems, so get out your calculators and let's go. Okay, so to solve these problems, we're going to need iceboxes. An icebox is a chart that's used to determine the initial amounts of products and reactants, their changes throughout the reaction, and their values at equilibrium. Type 2 and Type 3 equilibrium problems utilize iceboxes because all of the equilibrium values are not given in the problem. So we're missing some information. So we're going to have to figure out initially what was there, what the change was, and at equilibrium what's left. So here's our first example. 1.000 moles of nitrogen and 1.000 moles of hydrogen were placed in a 1.000 liter flask at 500 degrees C and allowed to react. Now, what you need to remember about the temperature is that as long as it doesn't change, it's not important at all. You can completely ignore it. And also remember that we're looking at Kc, that's concentrations. So this 1.000 moles is really not important. What we need is the molarity, that's moles divided by liters. But since it's in 1 liter container, a 1 mole in a 1 liter is going to end up with 1 molar. So after the system had reached equilibrium, the flask was found to contain 0.921 moles of nitrogen. Find the equilibrium concentrations of the other two. So initially, at the beginning of the reaction, there was a 1 molar concentration of nitrogen and a 1 molar concentration of hydrogen. 1 molar because it's 1.000 moles divided by 1.000 liters. Also, initially the container was empty until you put nitrogen and hydrogen in it, which means at the beginning there was no ammonia. So we've got 1, 1, and 0. I'm going to take out these molars just so we're not going to crowd up the picture. So at equilibrium, we have 0.921 moles of nitrogen, again in a 1 liter container, so that's 0.921 molar, and that's at equilibrium. So what we're going to have to do, actually let me make that green. So what we're going to have to do is figure out how nitrogen changed, how hydrogen changed, and how ammonia changed throughout the course of the reaction. So here's when we're going to get a new color. So notice that nitrogen started at 1 and it lost some amount to get to 0.921. So in your calculator, if you have 1 minus 0.921, you end up with 0.079. So over the course of the reaction, nitrogen lost 0.079 moles per liter. So notice the coefficients in the balanced equation. 1 mole of nitrogen for every 3 moles of hydrogen. So 1 mole of nitrogen for every 3 moles of hydrogen, 0.079 moles of nitrogen for every 0.237 moles of hydrogen. So I got that 0.237 by taking 0.079 times 3, because 3 times as many hydrogens as nitrogens. I'm going to subtract the same amount. Remember when we were talking about equilibrium at the very beginning? Reactants always react and go away. So 1 minus 0.237 is 0.763. For the ammonia, notice that the coefficient is a 2 in front. So for every 1 mole of nitrogen used, 2 moles of ammonia are produced. So for every 0.079 moles of nitrogen used, 0.158 moles of ammonia are produced per liter. That's a gain for the ammonia because ammonia is a product, so it's being produced throughout the reaction. Make that better, plus sign. So 0 plus 0.158 is 0.158. So at equilibrium, there's 0.158 moles of ammonia per liter. And those are the equilibrium concentrations. The change is always related in a stoichiometric ratio. Or another way to say that is related to the balanced equation. Initially, you can have whatever you want in the container. but the change is always going to be stoichiometrically related based on the balanced equation, and then the equilibrium is going to follow from that change. Another problem. This time we're going to find K if 0.7 moles of C are formed from 1 mole of A and 1 mole of B placed in a 500 milliliter container. So notice we have a 500 milliliter container. The first thing I want to do is find the molarities, because these moles are going to trick you and you're going to think you have what you need and you don't. So I'm going to start with 0.7 moles divided by 0.5 liters. 0.5 liters. 0.7 divided by 0.5 is 1.4 molar C. And 1 mole divided by 0.5 liter is 2 molar A and 2 molar B. I just want to get those numbers right away instead of these numbers so that these numbers don't end up confusing me and making me forget. So, initially, at the beginning of the reaction, there was a 2 molar concentration of A and a 2 molar concentration of B. Initially, at the beginning, there was no C and there was no D because they hadn't been produced yet. Something happened, A, B, C, and D all changed, and then at equilibrium, the problem tells me that 1.4 moles of C are formed per liter. So notice that C had to have gained 1.4 in order to get to 1.4 from 0. And also notice that the stoichiometric ratio is 1 to 1 to 1 to 1. So if C gained 1.4, then D had to have gained 1.4 as well. 0 plus 1.4 is 1.4. For A and B, those reactants lost moles over time because the reactants were reacting to produce the products. So this is going to be a minus 1.4 and a minus 1.4. Within the change column, they're all related to the balanced equation, and the reactants are always going to be negative, and the products are always going to be positive. So 2 minus 1.4 is 0.6, and 2 minus 1.4 is 0.6. I'd be totally done if they were asking for the equilibrium concentrations, but in this case they're asking us to find K. So now we need that equilibrium constant expression, or the K equals expression. That's the concentration of the products divided by the concentration of the reactants. And plug in what we have. C is 1.4, D is 1.4, A is 0.6, B is 0.6. In your calculator you could just type 1.4 squared over 0.6 squared and you end up with 5.44. Remember that K is dimensionless, so 5.44 is your final answer and there is no unit. So this is the last type 2 problem. I want you to try this all by yourself. Pause the video now. Alright, hopefully you've paused the video. We're going to make an icebox, initially change equilibrium. 2 moles of NH3 are placed in a 1 liter container. The 1 liter is really nice so that I know 2 moles of NH3 is really 2 molar NH3. At equilibrium, 1 mole of NH3 remains in the 1 liter container. So that's it. That's all the information they give us. Do remember that at the beginning of the reaction there is no nitrogen, there is no hydrogen, so those are both going to be 0. And then let's look at the change. Ammonia obviously lost 1, so 2 minus 1 is 1. So based on the stoichiometric ratio, the balanced equation, a 2 to 1 to 3, if ammonia lost 1, then nitrogen had to have gained 0.5, because that's half of 1. And hydrogen had to have gained 1.5, because that's 3/2 of 1. So we're looking at that balanced equation to figure out the change row. Now we're going to try to find K. So K is equal to H2, wait, hold on, I want to start with N2 times H2 cubed over NH3 squared. Plug the numbers in. That's 0.5 times 1.5 cubed over 1 squared. 1.5 cubed times 0.5 is 1.69 divided by 1 squared is 1.69. There's K. Oh, that was a really bad box. And that's it. And that's K. And that's a type 2 problem. Are y'all ready for the type 3 problems? Let's go. So a type 3 problem is giving you even less information than you had before. Let's see what I'm talking about. 1 mole of CO and 1 mole of H2O are mixed together in a 1 liter flask. Since it's a 1 liter flask, that does me a favor and I don't have to worry about the concentrations are the moles and then we're done. So initially, there's 1 mole of CO and 1 mole of H2O. CO2 and H2 are both going to be 0. And that's it. We're not given any other information. So I know that there's going to be a change, and I know that the change is going to be related to the balanced equation. And also I can see that it's a 1 to 1 to 1 to 1 mole ratio. So the change for every single one of them is going to be the same, except that the reactants are going to lose that change and the products are going to gain that change. But otherwise the change is going to be the same for everybody. So if we have some number that we don't know, but that will be the same for everybody, then why don't we just call it all X? CO and H2O will both lose X amount. CO2 and H2 will both gain X amount. So that at equilibrium we have 1 minus X, 1 minus X, X, and X. So now we're going to solve or plug that into the K equals expression, which means we need a K equals expression. Here we have CO2 times H2 over CO times H2O. If we plug in the numbers that were given, 5.1 is equal to X times X over 1 minus X times 1 minus X. Hopefully when you look at that right there, X times X, that you see we could just as well say X squared. And 1 minus X times 1 minus X, we could just as well say 1 minus X squared. And if we do that, this becomes a much simpler problem. The math becomes easy because all I have to do is take the square root of both sides. So if I take the square root of 5.1, I will end up with 2.25. I'll put that up here so I have room. That's the square root of 5.1. If I take the square root of x squared, I have x. And if I take the square root of 1 minus x squared, I have 1 minus x. So now the algebra doesn't have any squared x's in it, and it makes it a lot simpler. Let's cross multiply. So this is going to be 2.25 times 1 minus x equals x. We're going to distribute that 2.25 into the parentheses. So 2.25 minus 2.25x equals x. Now we're going to add 2.25x to both sides. So 2.25 equals 3.25x. Now we're going to divide both sides by 3.25. So x is equal to 0.693. And that's my x. And so I feel like I'm done. Except, wait a second. It doesn't say find x. It says find the concentrations of all the species at equilibrium. So now, since I have x, I can plug that in to all these places within my icebox. So the concentration of CO2 and H2, right here, this is just going to be 0.693 and 0.693. But for CO and H2O, since x is 0.693, 1 minus x turns into 1 minus 0.693, which is 0.307. And 1 minus x turns into 1 minus 0.693, which is again 0.307. So that's actually my concentrations of reactants and products at equilibrium. For CO and H2O, they're both 0.307. For CO2 and H2, they're both 0.693. Let's try another one. It uses the exact same theories as the one before, so pause the video now and try it on your own. All right, I'm going to trust that you did that, so let's see what we have. We have a 1 liter container, so that's easy. 1 mole of hydrogen initially, So this is going to be a 1 initially. And 1 mole of iodine initially. Initially there should be no HI. That's all the information that we're given. So C and E are unknown. I do know that the reactants are each going to lose and the product is going to gain. And they're all going to lose and gain in a balanced equation ratio. So since it's 1 H2 to 1 I2 to 2 HIs, that'll be X, X, and 2X. So at equilibrium, I have 1 minus X, 1 minus X, and 2X. Now we're going to plug that into our K equals expression. K equals HI squared over H2 times I2. So 55 equals 2x squared over 1 minus x times, hold on, let me make that prettier. 1 minus x times 1 minus x. Hopefully you saw the same shortcut as we did before. 2 minus x squared is already 2 minus x squared. I'm sorry, 2x squared is already 2x squared. But 1 minus x squared, we could just do this. And when we do that, we could take the square root of both sides. So the square root of 55 is 7.42. The square root of 2x squared is 2x. The square root of 1 minus x squared is 1 minus x. Now we're going to cross multiply. 7.42 times 1 minus x equals 2x. Now we're going to distribute the 7.42 in. 7.42 minus 7.42x equals 2x. Add 7.42x to both sides. 7.42 equals 9.42x. Divide both sides by 9.42, and so we end up with x equals 0.788. So, the question's actually asking find the equilibrium concentrations of H2, I2, and HI. So if x is 0.788, 1 minus x is going to be 1 minus 0.788, which is 0.212. Same thing here, 0.212, and then 2 times 0.788 is 1.58. And those are equilibrium concentrations. Only one more to go. Okay, this last problem is going to be a little bit trickier. It doesn't look like it would be until you actually start working it, and then you'll see what I mean. So first of all, it's a 3-liter container. So 3 moles in 3 liters is the same thing as 1 molar. 6 moles in 3 liters is the same thing as 2 molar. Take care of that initially at the beginning so you don't have to worry and remember about that liter container. So initially at the beginning, there's 1 mole of H2 per liter and 2 moles of F2 per liter and no HF because it hasn't been produced yet. There's going to be a change and an equilibrium. So the change is going to lose 1x, and gain 2x. So far this looks just like the problem ahead of it. So you end up with 1 minus x, 2 minus x, and 2x. Now we need the K equals expression. K equals HF squared over H2 times F2. And let's plug that in. 1.15 times 10 to the 2 is the same thing as 115 equals 2x squared over 1 minus x times 2 minus x. Now maybe you can see why this one's a different type of problem. Because now there's not a perfect square on the top and on the bottom. So we're actually going to have to solve this out, which means we're going to have to FOIL what's on the bottom. 1 minus x times 2 minus x. It's first, outside, inside, last. So the first is going to give me, let's see, 2. And the outsides are going to be minus x minus 2x. And the last is plus x squared. So then 2 minus x plus minus 2x. Okay, well, this right here is going to end up being minus 3x plus x squared equals 115. Then we're going to take this and cross multiply. So we end up having 115 times 2 minus 3x plus x squared equals 4x squared. I got the 4x squared because that square has to distribute in. Square the 2 and square the x. So now I'm going to distribute the 115 and I'm going to solve for x. At this point, it's a challenge problem. If you can come into class with this problem completely finished, there might be a reward in your future. Okay, that's all we have about type 2 and type 3 problems. We'll see you again next time for KP.